There are many possible configurations of this new patented lock design, but here's what it would look like when integrated into a typical doorknob. You can see that the circular keyway remains covered by the green engagement discs when the key is not inserted. Here's a prototype whose components were all printed from resins using stereolithography. In order to prove functionality for all cut combinations, adjacent maximum and minimum bitting cut heights were used, which you can see by looking at the key profile. The version in this video has the locked and unlocked states positioned 90 degrees apart. You can see that the key is inserted in any position and engages the inner cylinder, which is then rotated and the key can be removed directly from the lock's new state. The process can then be reversed, returning the lock to its original state, and you'll notice that the inner and outer cylinder, once the key is removed, are locked relative to each other. Here's an exploded view of the prototype version that was just demonstrated. This is just one of many forms at which the patented concept can be implemented. The key has 6 points at which the 3 blue inner locking vanes would contact its surface. Each inner locking vane would be analogous to 2 key pins in a standard pin tumbler lock. There are 2 sets of 3 red outer locking vanes for each state, locked and unlocked, in which the key may be removed. They would be the equivalent of the driver pins in a pin tumbler lock. The green engagement discs are housed in the inner cylinder and cover the keyway opening when the key is removed. The discs are moved radially outward as the key is pushed in and engage the grooves cut into the shaft by the head of the key. When the key is fully inserted, it allows the key to rotate the inner cylinder. This view shows how the green engagement discs engage the key when the key is fully inserted. Here's a view looking into the keyway with the engagement discs pushed out as if a key was inserted. The discs not only engage the key to operate the lock, but also keep the elements and other contamination out, as well as making efforts to pick the lock much more difficult. As you can see, the 3 interlocking vanes are each offset 120 degrees around the circumference of the keyway. The tips of the vanes extend into the keyway where the contact with the key is made. In order to rotate the lock, each vane must be positioned correctly at both ends simultaneously for all the seams between the inner and outer locking vanes to line up with the shear line between the inner and outer cylinders. This configuration makes all current forms of non-destructive lock picking ineffective against this design, including raking, individual pin manipulation, or lock bumping. This shows a cutaway view of one pair of inner and outer locking vanes. The blue represents the cross-section outer cylinder, and the red is the cross-section inner cylinder. You can see that with no key inserted, the vanes cross the shear line and prevent rotation of the lock. In this view, the correct key is inserted, which aligns the vanes, allowing for rotation. The major advantages of this new design are the ability to insert a key at any angle, needing only to guide the key in the vicinity of the opening. The key can then be turned in only one direction, taking the guesswork out of which way the key must be rotated. Once the key is turned, it can then be directly removed without the need to recenter the key to an original position. It also provides a number of new innovative challenges to those trying to gain unauthorized access by means of lock picking. And from a visual aspect, the design has a radically new look, which opens up endless possibilities for marketing and brand recognition.